Hello and welcome to the last Homework 2 video. So today I'm going to explain and derive the heat diffusion equation for spherical coordinates. And I tried to draw it here, but this is just a section of a sphere, and we're going to see what the equation looks like at this point and then what it looks like down here in its projection image. Okay, so let's start with the change in volume. It's going to be dV, and this is going to be equal to r squared, or the radius squared, times the sine of theta, and then this is going to be d theta, dr, and then d phi. And then just like the previous videos, it's still the same energy balance, that the energy stored is going to be equal to the net heat flow plus the energy generated. So this is going to be the heat flow in minus the heat flow out plus the heat flow rate times the volume, and then the energy stored is still density times heat capacity times the change in temperature over the change in time, and then times the volume on this side as well. So for this section here, this is the net heat flow, but we need to find it in each direction. So this is going to be the net heat flow in the radial direction, in theta, and in phi. So looking in the radial, or the r dimension, we know from the previous videos that we can say that the heat flow at some position is going to be equal to the heat flow at the position that we know plus the change in heat flow over the change in position times the overall change in position. And we said over here that the net heat flow is the heat flow in minus the heat flow out. So the net heat flow of R is going to be the heat flow of the position that we know minus this term here that we just found, which is the heat flow of the position that we know plus the change in heat flow over the change in position times the overall change in position. And so this is going to simplify to negative change in heat flow over the change in position times the change in position. And we're going to do this for each of these dimensions. So we can do this with theta as well. So we're going to use this same process that we did up here. So I'm just going to skip those steps for the other two dimensions. But it's going to be the same process, but just with respect to each of their dimensions. And then for phi, the net heat flow is going to be negative change in heat flow over the change in position times the overall change in position. And now we can use Fourier's law here. Where it's the heat flux is equal to the negative thermal conductivity times the area times the change in temperature over the change in position. So for Fourier's law, this is going to be very, this is like the general equation. So we're going to plug in this Q for each of these terms. And then this dx, this can be any of these, so that we're going to use dr, d theta, d phi. So let's plug the Q's in for all of these. using Fourier's law, and I will rewrite them over here. So net heat flow so we first will factor out this negative d over dr. That way we have the heat flux by itself, and then when we plug in Fourier's law, this is going to be the negative thermal conductivity times the cross-sectional area, which is r squared sine theta times d theta d phi. And then we still need the change in temperature over the change in position. And then for theta, it's going to be a similar process. And before I do that, I forgot this dr over here. Here we go. Now we can move on to theta. So we're going to again factor out this front term of negative d over d theta. It's going to be multiplied by the negative thermal conductivity times r sine theta times dr d phi, and then this is going to be dt dr, and it's going to be multiplied still by this d theta term as well. And then I actually lied, because this should be r times d theta to get it out of polar coordinates. So now let's do phi. This is going to again factor out this negative d over d phi. We're going to multiply it by the negative thermal conductivity times r dr d theta, and then it's going to be the change in temperature over r sine theta d phi, and then it's all multiplied by d phi. So now let's plug this into this initial equation up here. So let me see if I can fit all of this in one go. This is the density times the heat capacity times the change in temperature over the change in time. And then this is going to be multiplied by the change in volume. So I'm just going to copy this down. Whoa, no. Maybe. Okay, just kidding. I can't copy that down. Okay, the volume was r squared sine theta d theta dr d phi. Okay, and then this is going to be equal to the net heat flow that we just found for all of these sections. So I'm going to copy these down. And then add all of these together. Okay, so that's the net heat flow, and then we need to still add the generation. So it's going to be plus the flow rate times the volume again, which we said is r squared sine theta d theta dr d phi. So this is the overall equation, but now we can simplify some things to make it look a little bit cleaner. Okay, so first, all of these negatives, because there's negatives here, 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 these are all going to cancel. It's going to be positive. And then all of these volumes, there, here, here, and at the end are all going to cancel. So I'm going to rewrite that. I'm just going to cut this part of the video so you don't have to watch me rewrite it, but that's all I'm doing in this step. Okay, so now we're left with this equation here. And now I'm going to divide this r squared sine theta by all of these. And I'll cut the video again, but that's just the only step I'm doing here to simplify it. And then this is the equation that we're left with. And note this part here, because r squared is differentiable, when we divide the r squared sine theta, we get the r squared in the denominator because the sine will cancel. And then the same thing in this section here, this r sine theta is differentiable, so that stays there because of this here. And then the r squared sine theta is in the denominator there as well. And now all these k's, we can factor all of them out because we know that the thermal diffusivity is equal to the thermal conductivity over density times heat capacity. So we can factor this out, and we're left with the change in temperature over the change in time is equal to alpha, which is the thermal diffusivity, times all of these terms. So it's going to be d over dr, r squared, change in temperature over change in position, times 1 over r squared, and then plus d over d theta times r sine theta, change in temperature over change in position, times 1 over r squared times 1 over sine theta, and then plus d over d phi, and then this is change in temperature over change in phi, 1 over sine squared theta times 1 over r squared, and then plus the heat flow rate over density times heat capacity. This is the final equation for the heat transfer. Okay, so like I said, this is the general heat diffusion equation for a sphere. And then looking at this example, it wants to look at a case for steady state. So this is going to be 0. And no heat generation. So this is the heat generation term. That's 0. And we're only going to look in the radial direction. So we only want to focus on this part here. So let's rewrite this again. So this is going to look like 0 is equal to the thermal diffusivity times d over dr times r squared, change in temperature over change in position, times 1 over r squared. And then, because it's equal to 0, we can divide this over and then multiply the r squared over. we're going to end up with this expression here, where 0 is equal to d over dr of r squared, change in temperature over change in position. So now we can integrate this. The first time we integrate, we're going to end up with r squared dt over dr plus some constant is going to be equal to 0. And then that leaves us with c1 is equal to r squared dt over dr. And then we can rewrite this to have dt over dr is equal to some constant over r squared. We're going to end up with dt on this side being equal to some constant over r squared times dr, and then we will integrate both sides. And then before I do that, this should be negatives here, and then this should be from the initial temperature to the final temperature. This is the initial radius to the final radius. So after we integrate, we're going to end up with final temperature minus the initial temperature is equal to some negative constant times 1 over our final minus 1 over our initial, and then this negative sign will be distributed. So this is going to be, I'll rewrite it as delta T. The change in temperature is equal to some constant times 1 over the initial radius minus 1 over the final radius. And then we can solve for C1 is going to be delta T over 1 over the initial radius minus 1 over the final radius. And then, like we did in the previous videos, we're going to relate this to Ohm's law, where we have change in voltage is equal to the current times the resistance. And remember, in the last videos also, we related this to Fourier's law. We said that the heat flux is equal to the negative thermal conductivity times the area times the change in temperature over the change in position. And then we know that the area is 4 pi r squared. That's the area of a sphere. So we can plug that in. And then this change in temperature over change in position, we have that here, and we just solved for C1 down here, so we can plug this in as well. It's going to be times change in temperature over 1 over the initial radius minus 1 over the final radius. And this is all divided by r squared. And then these r squares cancel, and we're left with this expression where the heat flux is equal to the negative thermal conductivity times 4 pi times the change in temperature over 1 over the initial radius minus 1 over the final radius. And then relating it back to Ohm's law, again, like in previous videos, we talked about how the change in voltage is similar to the change in temperature, and how the current is flowing around a circuit is similar to how heat flows. So to find the resistance, we can rewrite this over here like this, where the resistance is going to be equal to the change in voltage over the current. And so we're going to do the same thing over here. We eventually want the change in temperature to be over the heat flux. So we're going to have that the change in temperature is equal to the heat flux times 1 over the negative thermal conductivity times 4 pi. And then this is going to be multiplied by 1 over the initial radius minus 1 over the final radius. And so this part here is going to be the thermal resistance. So I can just rewrite this by dividing the heat flux there. So now we have the total thermal resistance for heat transfer for spherical coordinates.